First of all, I would like to apologize. Yesterday, what happened is I was on phone immediately after our class, and the entire session was recorded perfectly. But during the saving, I was on phone, so I kept canceling a lot of things, and in the process, I also canceling the saving. So that's the predicament that got us. So we don't have yesterday's recording. But if you are not in class yesterday, please feel free to ask any question that we may have covered. And then based on what I've seen the content, we won't be able to complete all the content. But since the 3 days was just for recap, I think we've refreshed our minds, juggled our minds enough. And after today's session, we'll be ready for our Saturday classes. So it was just to trigger and bring back the machine learning genie in you. Most of you guys were either walikuwa na bangaiza tu, talking about Corona, talking about job losses, as in, there was so much to talk about. Machine learning was the least or the last thing you're talking about, but now we are back. We need to get used to the new normal, as it said. So, karibu sana. Let me share the slide where we were at yesterday. Can you guys see?
Not yet. Oh, yes.
You can see, yeah?
Yeah.
Okay,
Yes.
so as of yesterday, we went through oh, sorry, man. I've just seen a message from one of us. He's lost his nephew, Georges, so he won't be joining us. Too bad, man. I'll reach out to him after the class. Okay, for those guys who have joined today, we went through regression. I'll just give me 5 minutes to just go through what we covered yesterday for the sake of guys who are not there. So it won't be intense as it was. So we went through, it was actually quite a lot, yeah? We left at polynomial regression. Eric, you didn't make it yesterday, yes?
Yeah, I didn't.
So the last, we covered with you polynomial, yeah? Had we covered polynomial or we just took a break? Yeah, I think we covered polynomial. We started from here. So we went through the methods of building models, all in backward elimination, forward selection, bidirectional elimination, and score comparison. So I won't go through them. Just be aware that this is something that we jogged our mind yesterday. And we also saw how to do the code for building a regressor. We checked on polynomial regression and how it's different from the other simple and multiple linear regression. Looked at the graphing, the code as well. We also looked at a support vector regression and how it operates. We looked at quite a number of stuff with regards to support vector regression. Okay. There is also the visualizing of the same. We looked at decision tree regression. I looked at the decision tree as a class for classification. Decision tree, we looked at it and briefly discussed about how it can be used as both as a classifier and a regressor, but dwelt on decision tree as a regressor for that class, how the splitting was being done and how the algorithm works, and how the decision tree is built as the splitting is ongoing, and how the values are derived based on the splitting. And final decision, what we call terminal leaves. And then we looked at the code for building a decision tree regressor and how to make the prediction, plotting it visually. Random forests, we also briefed random forest and the steps for the idea or the concept behind the random forest regression, the code itself, and how it's predicted, how you do predictions using a random forest. We also plotted the random forest output. And then today, we start on evaluating regression models using the evaluation metrics available. Okay, so what we've understood so far about regression is there is always a line of best fit. Somehow that is what we are trying to determine. And using ordinary least squares method, the best fit is normally the line that has the least sum of squares. So basically, you try and get the residuals and determine the difference between this. Okay, assuming the red plots are the point, our data points, and our prediction line, which is line of best fit, is the black one. So we want to see by how much did we miss this target, each data point, by how much did we miss. For this one, it was on point, but for the others, we missed some by a greater distance like this one, but others by a small margin. So this difference here is the error. So the sum of cumulative errors constitutes our metric. So if this sum is big, it means what basically our model was doing was guesswork. But if it is small, then it means it is optimal. So the objective is always to have a smaller sum of residuals, of errors, sum of errors. Now, if we pick, for instance, if we did not consider this line of regression and just plotted an average. So we're saying like, we are doing an average of the data points. This is how it would plot like if it was an average of the data points. So this is normally called the total sum of errors. So the total sum of errors, you instead of looking at an average, so for instance, we're in a class and total sum of errors is equivalent to, we're in a class and we want to see the average age of members in that class. That is our target variable. So we could sum up all our ages and divide by the number of people in that class. So definitely we'll get an average, but the younger guys would made look like they're very old, and the older guys would be made look like they're very young. It will be a good thing for the old guys. Of course, someone like me who is a dinosaur. So if someone tells me I'm 18 years old, just because most guys in a classroom are between 16 and 28, I would agree. But how about someone who's younger? You're telling them, or especially a lady, in this case, say, wacha tusikie sauti ya Karo. Unaambia Karo yuko 45. Karo, how would you feel?
Unamtoa kwa market mapema.
So you see, namtoa kwa market haraka sana. So you see, we as guys, we might be doing some predictions, but the impacts of our models is only known to the consumers, the people using the models. Yeah. So the total sum of errors would look like someone just going the average, but there is normally a metric called R squared. So R squared is if you want to understand it based on a formula, it's normally you look at the sum of the total sum of residuals. Total sum of residuals, and you divide by the total sum of errors. Like now, based on your prediction, you get this value, and you divide by this one, the average. So more often than not, this average is always big because you've not tried to optimize by reducing the error in any way. You just guessed. So more often than not, the denominator is big. So if this denominator is big, and you try and reduce this value, because that is what your model is trying to do, by getting the line of best fit, whatever you get through this division will be definitely smaller. It's a fraction. So r squared is 1 less whatever you get. And that is based on the formula. But it's normally, in English, it normally reflects, the contribution of the features to your prediction. Yeah. So it's a standard metric that is used for regression. And there is another one called, who can tell me? Kuna r squared na kuna gani ingine? Yeah. If you keep quiet, we can keep quiet mpaka 6 and then we close. It's okay.
I was about to say squared r squared, then I remembered no, that's not its name. There's a certain r squared. Does the name start with an A?
Yes, it does.
Adjustable or adjusted.
Yes, adjusted r squared, yes. Yeah, now the second one is adjusted r squared, and it's built on the promises or the gap of the gap created by r squared. So one thing is, for as long as we are optimizing our line of best fit, r squared will always increase, whether or not we add features. So if you're adding a feature that is completely bogus to your model, r squared will still increase because it is working with an optimized sum of residuals. The numerator is optimized. So you're trying to get this to be smaller. So for as long as this one is smaller, yeah, then this fraction will be smaller, and 1 minus a smaller fraction will be a bigger value. So r squared will always increase. If we look at this, the added coefficient and the one that has been in a box. If for as long as b is greater than 0, then this feature adds to the value with a constant what's it called? With a constant denominator, then r increases. So whether or not, and you see with machine learning, especially when you're working with a domain that you pretty well understand, and you might know very well as a domain expert that this feature is bogus. We really don't need it. But if you are working with a team that feels they're not in the domain expert and they're stubborn, they just want to insist for it to add, and you rely only on r squared, then they'll beat you to your own game. They will actually say that, you see, r squared has increased. So what did you mean that it's not important? So because of that, we introduce one that actually considers, it's called adjusted r squared. That it's that one penalizes. Okay. It penalizes bogus features. Yeah. This one is number of the features. So if you have a sample and you add a number of features, if you increase this value essentially is going to be, we could work with arbitrary numbers. For example, if p equals to n, let's say it's 20, and then p is 4. Did you guys write that number somewhere? So if n is 20, 20 minus 1 is 19, and then 20 minus 4 is 16, minus 1 is 15. 19 over 15. So 19 over 15, you get your previous r squared. So what this will do if you increase a feature here, this value, the entire value here, if you increase the denominator, what happens? If you increase the denominator, what do you get? Do you get a smaller value or a bigger value? Say take 1 over 2. Is 1 over 3 bigger than, okay, no, 1 over 2 is not a good example. Let's say 1 over 5. Is 1 over 6 bigger than 1 over 5 as compared to 1 over 4? Which one is bigger? Between 1 over 4, 1 over 5, 1 over 6, which one is bigger? Between those three functions.
1 over 4.
Exactly, 1 over 4 is bigger. So if you decrease the denominator, you get a bigger value. Yeah? If you increase the denominator, you get a smaller value. So that smaller value, yeah, multiplied by a smaller value, you get a smaller value and it will reduce. But if you increase it, and the impact of that, if you increase it, it becomes small. Small multiplied by a smaller value, this one increases. So smaller value, so it could be 0.2, you'll get 0.8. Adjusted R squared increases. So this is a formula within which you can penalize features that are not relevant. So if the feature that you add has a coefficient that is not the algorithm detects that is not relevant, then adjusted R squared is affected. So it is normally close to R squared, but not the same. All right, I've spent quite some time there. On the next slide, the pros and cons for regression algorithms. It's good to know them. Yeah, some of the assumptions. The one downfall about regression is the assumptions are not realistic. It's not always the case in the real world to get linearly related variables or independent variables that, okay, not one variable not correlating to another. So the assumptions are sort of like a disadvantage to linear regression. Polynomial regression, choosing the right degree or ordinal is a challenge. You need to balance between variance and bias. I think the variance trade-off, we didn't cover them in class, but we will cover that. So it is important to know the pros and cons of all the algorithms that we've covered and why we need to choose which one. Okay, so that's it for regression. This is what we were to cover yesterday, but we had to cut it short. Any contribution to what we've covered, questions before we quickly move to classification? Any query?
I have one.
Yes.
You were to clarify something on decision tree and random forest. You were to get a pictorial aid or something.
Oh yes. Pictorial on how the decision flows.
The leaves and the now the difference, to understand the difference between the trees, to count the trees and how they relate with the leaves in the decision tree.
Okay, it was in one of the slides that I used. I think I'll just have to pull it. Let me just pull that slide right now. Okay, Carol. Can you see this slide? Guys, can you? I hope you can see the slide.
Yeah, I can.
So, random forest, look at the image to your far. Is it left? It's confusing because I'm looking at it and then you guys are also looking at it. Yes, far left. Yes, okay. So, random forest simplified. That's this the image I want us to look at. So you see, it's a collection of several trees. So there is tree 1, and there is tree 2, and there is tree n. So it can be several trees. And based on the explanation we gave yesterday on how those decisions are being made within a tree, on the splitting, which is done by the algorithm. So within the algorithm, it does certain splits. And for the prediction within that split, it's like it's creating cells. And then the prediction for a new value within that split becomes the average. So this tree would come and make a certain prediction that this new data, following that splitting, I choose that it is of class A. And then this tree would say, okay, I followed this path, and I also came up with a decision, which is class B. And then tree N follows another path and says, okay, me, according to my splits, I think it is a class B. And then, okay, at the end of it all, random forest algorithm, through the N estimator, if there are 10, those are 10 trees. So there is some sort of like voting. How many people said class A, how many people said class B? And then the final class is determined. In this case, this prediction would be a class B. Carol, does it make sense?
Yes, it does.
Yeah, and it's the same thing on this other side. So these are several trees, and then the final prediction is class 1 is 1. So that is how it works. So decision tree is just, random forest is just a collection of several trees. And once you understand the concept of a decision tree, random forest would be easier. But like I mentioned, there are several other terms that you need to be aware of, like information gain and others that we covered some of them in class, but through our projects, this will definitely come much, much more clearer. Okay, I'll need to go back to our slide.